here, so I'll say snowy day. My name is Ryan Abramowitz. I am the student museum assistant. I'm a senior at TCNJ and an art history major, and it is my pleasure to introduce Dr. Jonathan Allen. And I have a lovely picture of him here that his wife so kindly uh, took and provided for us to share. So Dr. Jonathan Allen received his Ph.D. in applied physics from Washington University in St. Louis. And since then, his career has mainly been in solar photovoltaic R&D and industrial RF power systems. He's worked with electronics for at least 60 years, and he is currently an independent consultant in industrial RF and instrumentation. For the past 8 years, Dr. Allen has been a volunteer at the Sarnoff Collection, restoring and documenting electronic artifacts, lecturing and guiding visitors. And so in this talk, Dr. Allen's going to begin with the earliest history of vacuum tubes, describing the Edison effect and how Ambrose, Fleming, and Lee DeForest inventions exploited this to create the first functioning vacuum tubes. We'll then go into a review of the basic theory of tubes as we move on to the pioneering developments at companies like GE, Bell Telephone, and RCA, including Edwin H. Armstrong circuits. These creations revolutionized communication and led to our modern age of electronics. And I will now end my screen share and give the floor to Dr. Allen.
Okay, let me just get things set up here a minute. Okay, well, thank you for your excellent introduction there, Ryan and Margaret. We're going to limit ourselves to the early history of vacuum tubes, and then limit ourselves to receiving tubes because we only have a finite time here, and if the material we're talking about could in fact fill volumes, and in fact it has. If you take a look at afterwards at our bibliography that I posted. Also, since we have a general audience, I'm going to go easy on the math and physics. And finally, since the Sarnoff Collection is sponsoring this lecture, my discussion of industrial developments will concentrate on RCA, although there were other companies involved in this business. So let's get started. Until the invention of transistors and integrated circuits, we hunted with stone tools and ate raw meat in caves. And the fastest communication was by a guy on a horse. Well, at least that's what a lot of youngsters seem to think. The fact is that from the early 20th century until at least the 1960s, vacuum tubes dominated electronics, and they enabled us to evolve most of the circuits that we now build with solid-state components. And interestingly, this includes both analog or linear and digital functions. So how did it all begin? Well, literally, as well as symbolically, it started with a glowing light bulb. Although some early 19th century physicists had observed that when a negatively charged conductor was heated to incandescence, its charge dissipated, it was Thomas Edison who first documented the thermionic emission, which we have named in his honor as the Edison Effect. In 1875, shortly after he had invented electric lamps, Thomas Edison observed dark deposits on the interior of his lamps. This, of course, was evaporated filament material, which at that time was carbon. This was before they knew how to make filaments out of tungsten. But what was curious was a shadow in the deposit that lined up with the positive end of the DC filament. He ran the filaments, as you know, on 110 volt DC. Somehow, the effect, this deposition, was influenced by electric fields. So Edison, being the curious chap he was, installed a metal plate inside the evacuated bulb so it faced the filament. He observed that if the face was positively charged with respect to the filament, a current flowed between the plate and the filament, but not if it was negatively charged. He patented the effect. As you probably know, Edison tried to patent anything he came up with, and he published the findings in 1883. Of course, there was still no physical theory to explain what was going on, nor did Edison have any clear idea of how he might exploit this for any useful purpose, but he patented it nonetheless. Then in 1897, English physicist J.J. Thomson discovered the electron, measuring its charge to mass ratio and identifying it as the carrier of electric current. At the same time, Heinrich Hertz's experiments demonstrated the electromagnetic waves that James Clerk Maxwell had predicted in his theory quite a few years before, in the 1830s. And shortly thereafter, Marconi began developing practical wireless communication. Thus, radio and electronics approximately share a birthday. The biggest problem facing early wireless was that there was no way to amplify a weak signal, and even detection was difficult, relying on coherers, magnetic detectors, and galena crystals. Incidentally, the galena crystal, if you want to be technical, is a solid state detector, but they didn't understand the theory at the time. And as wireless communication tried to cover greater and greater distances, the inverse square law, which says that the intensity of the signal falls off the square of the distance, was taking a heavy toll on the ability to receive the signal. The next big improvement was in January 1904, when John Ambrose Fleming in England, building upon Edison and Thomson's discovery, exploited the one-way conduction of the Edison effect to rectify and thereby detect radio signals. And here's the Fleming valve detector. For those of you who are familiar with the crystal set, this circuit is almost identical to that of the crystal set, except that here you have the signal coming in the antenna. It couples into a tuned circuit with a variable capacitor and an inductor. And instead of going through a galena crystal, it goes through this vacuum diode, the Fleming valve, and then into headphones. This capacitor has a low reactance at radio frequency, but a high enough one at audio that you can hear the signal. Now, since Fleming's diode allowed only a one-way flow, it suggested the check valve that is commonly used for fluids. This is the valve with a flapper, such that the fluid can flow in one direction, but it closes if the fluid tries to run in the other direction. And hence he named it a valve. He called it the oscillation valve, but the Fleming valve seems to be the name that stuck. And by the way, to this day, the Brits call vacuum tubes valves. The valve eliminated the tweaking of the cat's whisker needed to operate the galena crystal and had better rectification. But still, this was detection without amplification. In that same year, a fellow named Wenelt in Germany found that coating the thermionic filament with either calcium oxide or beryllium oxide could increase the emission. There's how much current of electrons you could emit. We now know that thermionic emission occurs when the thermal energy of the most energetic electrons exceeds the binding energy that holds them to the conductor, and we call this binding energy the work function of the cathode. The coatings reduce the work function and therefore allowed more electron emission. We'll get into this more a little bit later. Well, after the success of the valve, scientists and engineers recognized that the next big step would have to be amplification to receive the weak signals from afar. There were numerous inventions and battles between inventors over priority and infringement, so attribution is often unclear. Some early attempts let the signal control a deflection or focus of a cathode ray so that the electrons would either strike or miss a conducting target. That never really worked well. Anybody who's worked with the cathode ray tubes in an oscilloscope knows that it takes a pretty substantial voltage to deflect the beam. And we were trying to detect very small voltages of millivolts. Meanwhile, in the US, a scientist engineer named Lee DeForest was experimenting with his version of the valve. And he noticed something funny, that electric fields imposed from outside the bulb could alter the diode current. What if the field was put inside the bulb, actually in the path of the current? A solid sheet of metal would work, but in a sense, but a solid sheet of metal would block the electron flow completely. But what about a grill that resembles the gridiron of a barbecue? Ah, that would be the way. And he called it a grid. And to this day, we call it a grid. And it turns out he was right. So in 1906, he patented a vacuum tube that he called the Audion. And here you can see how it works. Here we have a battery powering the filament. Here you have your hot filament. You make one electrical connection to one side of the filament. Here, between the here's your grid, and then you have your plate to collect the electrons. This is just a schematic type of layout. Here we have a photograph of an actual early Audion. And if you look at it carefully, you will see that close to you, you have this zigzaggy filament. Behind that, you have the zigzaggy grid made out of metal wire. And behind that is the plate. And here's the base where you screw it in. By the way, this is not as big as it looks, because this is what's called a candelabra base. It's not as big as a standard Edison base we use on most bulbs. So anyway, as a detector, the Audion did provide gain above what a simple diode could do, but it could not amplify in the modern sense. Here's a circuit that DeForest applied. It resembles what we saw before. The signal comes in the antenna, goes through a tuned circuit, an LC tuned circuit. You tap off that and couple into the grid of the tube. And by the way, the early version did not have a grid leak resistor, and that was a serious problem. I'll explain that in a few minutes. And then coming off the plate, where you have your amplified signal, it goes through your headphones and into the positive side of your B battery. By the way, in radio and electronics, the A battery is the low voltage battery that lights the filament. The B battery is the high voltage that powers the plate and other electronic parts of the tube. And they sometimes have even a C battery, which provides a negative bias voltage to the grid. Anyway, the Audion detector had problems, the worst of which was that there was a soft vacuum. The vacuum in the Audion kind of sucked. Actually, it didn't suck well enough. There was something on the order of 1 millimeter of mercury, or a tenth of a millimeter of mercury pressure of residual gas in the tube. And as a result, the electrons trying to find their way from the filament to the plate would bump into gas molecules, ionize them, and you get an ion flow in this direction and an electron flow in this direction, and the two are bumping into each other, and it just wasn't happy at all. Second problem is that he did not have this grid leak resistor, and hence there was no DC path off the filament. So the filament could float to whatever voltage it felt like as a result of electrons striking it or falling or getting knocked off it. And so the tube didn't know where in its operating curve it was happy. The geometry was certainly less than optimum. And the tube was, the Audion was unreliable, the short life, and in part this must have been due to the poor vacuum, because the ions that would slam into the filament would dislodge metal from the filament by a process we now call sputtering, and erode the filament away. You erode away enough filament, burns out, and you're out of business. The mechanical structure was fragile, but the most serious problem was that de Forest did not understand the theory. For example, he believed that a perfect vacuum could not work. He couldn't conceive of electric current passing through absolutely empty space. Now, perhaps you can excuse him because the electron was discovered only 8 years earlier, and Thomson's papers were published in the physics journals, not in the engineering sources that de Forest might have read. But let's make sure we know the theory. So let's get into it for a moment. In a diode, the hot cathode emits electrons by what is called a thermionic or Edison effect. In a conductor, some electrons are not bound to individual atoms, but are free to wander within the conductor. And by the way, this is how a conductor conducts. If they migrate to the surface, however, there's a binding energy called the work function that prevents them from drifting into the space around the conductor. If, however, one raises the temperature until the most energetic electrons have a kinetic energy greater than the work function, then they can escape, especially if there's a positive field outside to attract them. Remember, the temperature is the mean kinetic energy of the particles in a system. The positive anode of the diode accomplishes this field, and the anode or plate, and we in the vacuum tubes we use the term anode and plate almost interchangeable. The anode, however, is not hot enough to emit electrons, so the diode will conduct only when the plate is positive with respect to the cathode, and this is rectification. Simple enough, but there is another, more subtle but vitally important effect, which we call space charge. No, this is not a command given to space cadets. The electrons leaving the cathode have a negative charge, and they're migrating through the space to the anode. They're traveling pretty fast, but only a minute fraction of the speed of light, maybe about 1 or 2%. And therefore, they are, from the point of view of electromagnetic fields, can be seen as being essentially at rest. So here we have a bunch of negative charges between the cathode and the plate. They, in fact, these in fact cancel some of the plate's positive field as seen at the cathode surface. And this limits the current to a lower value than what the cathode actually could emit. So that's what space charge does. Let's look at space charge in a triode now. And we're going to take a little peek ahead. The grid is now located quite close to the cathode. And applying a negative grid voltage enhances the space charge effect by making it by its negative potential. The more negative the grid, the less plate current, until finally you reach a point called cutoff when the current actually reaches 0. Now, if you set the fixed DC voltages on the grid, which we call the bias, in a range that reduces but does not cut off the plate current, then superimposing input signals on the grid will modulate the plate current. And it turns out that a very small grid signal can have a big effect on the plate current, hence amplification. And by the way, when I say a small signal, for good performing tubes, we're talking about microvolts, millionths of a volt, the level at which even faint radio signals come in from the antenna. Now, the next series of developments surprisingly came not in wireless, but in wired communication, the telephone. Phone companies, specifically AT&T, often known as Ma Bell, these phone companies were trying to extend the range of long-distance calls. ATT set itself the bold goal of a transcontinental telephone line. Now, the company had been extending range with using heavier copper lines and impedance matching loading coils invented by Oliver Heaviside, but you can only go so far in both senses with these techniques. They hoped to demonstrate the line for the 1915 Trans-Pacific Exposition to be held in San Francisco, but they knew it would take a technical breakthrough using amplified repeaters spaced along the route. The concept of a repeater was not really new. The telegraph had been using repeaters for decades in the form of the relay. And just to explain, just briefly, let me explain how the relay would work at a telegraph. Here's a weak signal coming in from a faraway station upline. And when it comes in, it goes into a coil that is wrapped around an iron core. These are the standard schematic symbols. The iron core pulls in a magnetic armature, which closes this contact, and the higher voltage from the battery then propagates out the line to the next station down the line. Well, the relay is great for the telegraph, but it has a fundamental problem. It is either on or off. There's no in between. We would today call it a digital device. And by the way, some of the early digital computers did use relays as logic devices. Phones need a linear amplifier where the output is proportional to the input. Now, DeForest, by this time, had made some improvements in the Audion, but it was still not up to the job. Nevertheless, AT&T saw its potential, so their Western Electric Research Facility, which was to become Bell Labs, obtained a license from Lee DeForest in 1912 with the intention of developing the Audion into a telephone repeater to extend the range of long-distance telephony. There, a team of researchers headed by Dr. Harold Arnold began a dedicated program to perfect a truly practical triode amplifier. And in some ways, the job was a little bit easier than radio because you were dealing with audio frequencies, which are much lower. General Electric initiated a parallel program with Irving Langmuir, who was already a fairly famous physicist. The first challenge was high vacuum. Arnold, and especially Langmuir, realized that residual gas was not only unnecessary for electron flow, but was in fact bad. Both teams exploited the advances in vacuum pumps to get a hard vacuum in the range of 10 to the minus 6 or 10 to the minus 7 torr. Let me explain the torr. The torr is named for Evangelista Torricelli, who in 1643 invented the mercury barometer. And the barometer measures pressure in millimeters of mercury. And here we use the torr because when you get down to the lower pressures, it would be less than a monolayer of mercury. Anyway, let's think about this. 10 to the minus 6 torr is 1/1,000,000th of a torr. An atmosphere is 760 torr, in the order of magnitude of 1,000. So 10 to the minus 6 torr is 1/1000,000th, that's with a B, of an atmosphere. And if you get down to 10 to the minus 7th, it's 1/10,000,000,000th of an atmosphere. In that kind of a vacuum, it's virtually a perfect vacuum because an electron can travel many feet before it bumps into an air molecule, and with the possibility of ionizing it. They also improved the geometry. Langmuir at General Electric in 1913 brought rigorous physics and vacuum technology to bear and advanced the theory of electron physics in tubes. He proposed the theory of space charge, which we talked about a little bit earlier, and the 3/2 power law for space charge limited plate current versus voltage. That is, if you're in the space charge limited region of the tube's current voltage curve, and you raise the plate voltage, the current will increase to 3/2 power. That is more than linearly with voltage. The research team's work improved the triode with a concentric geometry. Here we can see this. The grid and plate are concentric cylinders, and they replaced de Forest's inline arrangement. Also, as I pointed out earlier, locating the grid close to the cathode improved its control of electron flow by being able to modulate the space charge. The mechanical structure became more rugged, and a coated filament yielded better efficiency and longer life. And when the tube finally had to be replaced, it now had a plug-in base. Here's a drawing of a concentric triode geometry and a perspective drawing. And here you have the cathode in the middle, the grid, the plate, and around it the glass envelope, which keeps all that super duper vacuum inside. The amplifier, they realized that the amplifier tubes, the amplifier circuits for the tubes now had to have a DC path, a grid leak resistor to define the grid bias and keep it in the most linear part of the transfer curve. And fortunately, the grid leak resistor can be in megohms because the current into the grid is virtually nil. The contributions of Arnold, Langmuir, and their dedicated teams finally perfected a triode suitable for the sought-after amplified repeater. They tested it in 1913 between New York City and Philly, which means it must have come right past where we are, a distance of 100 miles. And thereafter, AT&T rushed to build the transcontinental line between New York City and San Francisco. And here we have the completion of the transcontinental telephone line at the Nevada-Utah border, with a line coming in from the west and a line coming in from the east, got spliced together by that brave fellow up the pole with his climbing spikes. And the witnesses are standing on the ground cheering for him, and he's got a flag flying and all that kind of stuff. The event somewhat is reminiscent of the driving of the Golden Spike for the Transcontinental Railroad decades earlier, which was also a great engineering achievement. The opening of the line, concurrent with the International Exposition, took place with great fanfare on January 25th, 1915, so the anniversary, I think the 107th or something anniversary would have been celebrated about a few days ago, because we're just less than a week past that. The event, widely publicized, also established the vacuum tube as a reliable reliable amplifier, as a reliable amplifier. Other inventors discovered that the triode could be an oscillator. Just as the escape in a clock replenishes the mechanical energy losses in an oscillating pendulum or balance wheel, the gain of a triode with positive feedback could do the same, and to create for an oscillating LC, inductor capacitor circuit. And the first practical oscillator is generally credited to Edwin Armstrong, although Alexander Meissner also conceived of the idea independently. And here we have the circuit of the Armstrong oscillator. Here's your triode with the filament and the battery that lights the filament. You have a tuned circuit that sets the frequency, the square root of the product of inductance and capacitance sets the angular frequency. And here, when you come out of the plate with the amplified signal, you go through another coil, which is called a tickler, which is inductively coupled, hence the transformer feedback, into the oscillator coil with the provision so that it is in phase. So that as the grid goes down, the plate goes up, and then this drives the grid down further. And it sets it swinging, almost like pushing a swing as it swings. And here we have the RF bypass over here, and finally the B battery, which drives the whole thing. As I said, the Armstrong, also called the Meissner oscillator, used a transformer inductive feedback. Armstrong also experimented by tweaking the feedback levels to just below the threshold of oscillation. And this was quite spectacular because it resulted in a regeneration, as he called it, which raised the gain of the tube and negated any losses in this tuned circuit. So the selectivity became extremely high. It allowed one tube to have a gain of tens of thousands and extract even weak signals from the ether. By the way, I'm using ether as in a poetic sense. I know that Einstein and other physicists at the time discredited it. Anyway, the ability of one tube to achieve such enormous gain in selectivity was especially important then, since tubes were rare and very expensive. And here is the regenerative receiver. It resembles the oscillator very closely if you look. Here the antenna comes in through a coil. It couples into the oscillator circuit, just as it did in the simple triode receiver with the Audion. By the way, they call it triode because it's three elements: cathode, filament, cathode, grid, and plate. And then you've got your grid leak resistor, which defines the bias on the filament, on the grid. And then, of course, you've got the tickler that comes off the plate circuit. And in series with the plate circuit is your headphones, which allow you to hear the signal that you've received with all this gain and all that. It was very tricky to operate, but it worked. Armstrong had other inventions. In 1918, while working in the Army Signal Corps during World War I, Armstrong invented the superheterodyne receiver. And here's your superhead. The signal comes in through the antenna and goes through a relatively low gain RF amplifier, just to give it a little bit of a boost. And you can see the signal, the amplitude modulated signal comes in, and then it goes into an interesting circuit, which is another tube that functions as a mixer. And you operate the tube somewhat non-linearly, so that the signal from the local oscillator mixes with the signal from the RF amplifier, and you extract the difference in frequency. Now again, that difference frequency is constant no matter what frequency you tune your receiver to, because the RF amplifier, mixer, and local oscillator all track each other. So you can get all your selectivity in this IF amplifier without having to tune it every time you try to change the received frequency. The output of the IF amplifier then goes to a second detector, then an audio amplifier, and a speaker. You can see the IF gets amplified, audio gets amplified. And I said a speaker because now you've got enough gain that you can drive a loudspeaker, not just headphones. Initially, the superhead was to overcome the poor high-frequency performance of contemporary tubes, whose gain fell off markedly at frequencies above 500 kilohertz, the bottom of the broadcast band. But the superhead yielded such superior performance that even after high-frequency tubes and transistors became available, it still, to this day, dominates virtually all receivers. And incidentally, this is the same Armstrong who is also known for electronic broadband FM radio. Guy was quite a hero. We saw in the regenerative circuit that in-phase feedback can raise the gain of a triode, but negative feedback can suppress the gain. An unintended source of negative feedback is due to grid plate capacitance. As already mentioned, early triodes began to suffer serious loss of gain at a few hundred kilohertz. And by the time you reached a megahertz, the gain was approaching unity. So it was hardly amplifying at all. Now in 1920, a fellow named John Milton Miller first published a theory to explain this gain suppression by what we thereafter called the Miller effect. How does that work? Well, let's say this tube has a gain of 10, just to use some simple numbers. You drive the grid negative by 1 volt. Well, because the gain is 10, the plate swings positive by 10 volts. So the difference between the plate and grid now is 11 volts. If you do it the other way, it's obviously the same also. Now, if this capacitor is just, say, 5 picofarads, which is typical of tubes, that doesn't amount to much at low radio frequencies. But it gets multiplied by gain plus 1. So now you have the equivalent of 11 times or 55 picofarads. That's enough to knock the hell out of your gain. Now, radio kept wanting to get to higher frequencies because there was more bandwidth that you could exploit. You didn't have to remain in the crowded low frequency channels, and the higher frequencies had the advantage that they could cover long distances for better. But anyway, the remedy came in 1926 when a fellow named Dr. Albert W. Hull and his colleague N.H. Williams at General Electric put a shield or screen grid between the control grid and the plate to create the tetrode. That means 4 elements now, right? Tubes could now work at tens of megahertz, opening up a huge range of the radio spectrum. And as I said, this is especially the shortwave, by which ionospheric skip could allow transoceanic communication with moderate transmitting power. And here's a tetrode amplifier. Notice that the screen grid is very similar to what we had before, but the screen grid here is maintained by a voltage divider at a lower voltage than the plate, and it's bypassed to ground through this capacitor, a big capacitor, so that there's no AC allowed on that screen grid. And that totally blocks out any desire of the plate to couple back into the grid. Also about this time, tubes started using what is called the equipotential or indirectly heated cathode. That means that the potential is uniform over the whole surface of the cathode, unlike the filament, which sees a voltage drop, a voltage difference across it due to equal to the value of the A battery. But the cathode can now be at a voltage independent of the filament supply. It not only allowed the cathode, it also allows the filament to be run off an AC power supply, which is handy if you want to run plug-in radio sets. Because with the cathode isolated, the AC doesn't get superimposed on the signal and cause 60-cycle hum. As with the triode, the tetrode was made concentric in practical. So the schematic shows it in line, but it's practical. And here we have our heater. When it's not the actually emitting thing, it's called a heater rather than a filament, although people are sometimes sloppy and still call it a filament. Surrounding that is a ceramic, usually aluminum oxide, which conducts heat but blocks, but is an electrical insulator. And around that is the cathode, control grid, screen grid, and plate. Now, the tetrode still had a stability problem when used for handling high amplitude signals, which caused the plate voltage to swing below that of the screen. And here we have anode current versus anode voltage for a triode. And as you can see, it rises more than linearly. That reflects the 3/2 law that we talked about before. But let's look at our friend the tetrode. Everything starts out happy. There's a lot of gain, you can see, because a big change in anode current for small change in voltage. And anyway, all of a sudden, oh my gosh, it drops down and then climbs again. So let's see why. Under these conditions, and I'm now showing the plate has swung now to 100 volts, which is below the 150 that the screen's sitting at. By the way, the screen sometimes is running very close to plate voltage, which makes this problem even worse. But let's just use these numbers for now. Under these conditions, each electron that strikes the plate dislodges several secondary electrons, which now are attracted to the more positive screen. Their charge is thus subtracted from the charge of the electrons that are striking the plate. So there is a range where rising plate voltage causes a falling plate current. This is a negative resistance curve, which produces an instability and unwanted oscillation. By the way, there's even a circuit called the dynatron oscillator, which exploits this intentionally. So this sets some limits on how you could use your tetrodes. In 1926, however, the Dutch engineer Bernard Tellegen, T-E-L-L-E-G-E-N, added one more grid between the called the suppressor, and he placed it between the screen and the plate. And this is a very open sort of grid, and it was kept at ground potential or cathode potential. In fact, in some tubes, here we go, here's a suppressor. In some tubes, the suppressor was connected to the cathode internally. So it was always at cathode potential. This basically, now if an electron tries to leave the plate, it sees a negative charge over here, a negative zone over here relative to the plate, and it just returns to the plate, and it's as though it were never emitted in the first place. This led to a wide range of reliable, stable tubes capable of handling both high frequencies and high amplitude. Pentodes are versatile amplifiers for both audio and RF, and handling both signal levels and power amplification. This is a gadget I built. This is was a military surplus radar IF amplifier, and this has 5 high gain pentodes. For those of you who are into tubes, they're 6AK5s. And it's tuned to 13.56 megahertz, which is the industrial frequency that's used for industrial processing. Nobody uses it for communication because it's all polluted with industrial processing. But you still don't want the industrial process RF to leak too much. So this was used, I use this for snooping RF leakage of industrial systems. And when you crank up the gain, it has a sensitivity of microvolts and a gain of 1/2 million between the input and the output. And these shields on the tubes are necessary because if you take them off, just the capacitive coupling between the input tube and the output tube will cause this thing to break into oscillation. Now let's look at the bigger picture. We've talked a lot about research. Research and development is based on the principle that while research discovers theories which can lead to great inventions, it takes development through industry to commercialize those inventions and to make the products that incorporate them. And this is where the Radio Corporation of America, better known as RCA, actually now officially known as RCA, comes in. In 1919, after World War I, the US government realized that transatlantic and ship-to-shore radio communications was too important to the public good, we now call it national security, to be in the hands of the British Marconi Company, which was in fact a foreign firm. Even though the British were friendly, sharing patents with GE, they were still legally foreign. Therefore, the U.S. government intervened to help buy out American Marconi and establish RCA to take over their functions. RCA also acquired the cross-licensing agreement of patents and collaboration with GE. A further complication that they had to solve, though, was that GE and AT&T, Ma Bell, had patents on vacuum tubes that overlapped and prevented either from producing tubes without infringing on the other. The government, therefore, convinced all three companies to share their technology, quote, for the good of the public, unquote. In 1921, Westinghouse Company joined the cross-licensing agreement. It was under this alliance that General Electric's Schenectady Labs, Westinghouse, Western Electric, AT&T, and the new RCA company developed improved tubes such as the tetrode and pentode, while Westinghouse added manufacturing capability for the devices that might use these tubes. RCA introduced its first commercial tube radio receiver for ordinary people to use at home, the Radiola Senior, using Armstrong's regenerative circuit. At this time, RCA had no manufacturing facilities, so GE made the tubes at its Harrison, New Jersey lamp factory, which eventually became almost exclusively a tube factory over the years. Westinghouse manufactured radio sets, which RCA then marketed. And as you can see on this set, the Westinghouse brand appears on the lid. But eventually RCA put their own name on it. RCA did not make its own tubes until it bought out the Harrison Works from GE in 1930. If you look at this set, it's fairly simple to operate. In the upper left is the filament rheostat, which is essentially the volume control. Down here is the tickler adjustment, which is very tricky if you want to get lots of gain but not have it break into oscillation. And by the way, a good reason for it not to oscillate is that if it does, the oscillations go back out the antenna and cause interference to your neighbor's sets, and that doesn't make them at all happy. Here's the tuning control, and just peeking its little head out of the control panel is the top of the vacuum tube, and you can actually, when it's lit, you can actually see the filament glowing. It was later that RCA had acquired manufacturing capacity to make the radios themselves. Now, for customers who wanted a bit more volume, RCA offered the accessory amplifier, which shared the same battery set. And here we have the amplifier, and you can see once again the tubes poking their little heads out through the panel. As tubes became cheaper and more available, RCA introduced TRF, tuned radio frequency sets, that avoided the need for the critical tweaking of the regeneration. And one of them that we have at the Sarnoff Collection, although that it's not individually this one, is the Radiola 18, which has 3 tuned RF stages ahead of the detector. And this one was made in 1927. Some of these photos are courtesy of a fellow named Stephen Sostrom at the University of Michigan Technology Museum. And he was kind enough to let me use his photos that he had posted online. The Radiola 18 also was RCA's first line-powered plug-in set, so no batteries. Numerous other home radios followed, including superheterodynes, which, as I mentioned before, were also an Armstrong patent. RCA's first commercial superhead was the Radiola AR-812. But first, here's a look down into the Radiola 18, sorry. You can see these 3 tubes of the TRF stages. Here's a 3-gang tuning capacitor that drives them. And here's a detector, audio amplifier, and the rectifier tube for the plug-in power supply. Anyway, here, I'm sorry, the first superhet that RCA introduced was the AR812. And at that time, they did not gang together the RF amplifier and mixer and local oscillator. You had to tune them separately with these knobs here. And this loudspeaker was sitting on top of it. And finally, a significant radio was the Radiola 26, which is a 6-tube super heterodyne portable. This set is obviously a portable. I mean, just look, it's got a handle on top, right? Well, don't, before you laugh too much, remember that the boom box, which was so popular here in the age of transistors, when you could put a transistor right in your pocket, and people were carrying around boom boxes even bigger than this. But perhaps more interesting is the rotatable directional loop antenna. This is not a solid piece of wood. It's a 2 laminated sheets of plywood with a space between them and a coil between them, which is rotatable. So you can get maximum signal from the station you want to hear and tune it to exclude a station you don't want to hear, so long as it's off in a different direction. Those radiolas and other reliable receivers, along with the growth of broadcasting, brought radio into homes throughout the industrialized world. People could now listen to music, to lectures, to sports events. Flory, who was the curator until very recently, gave a talk about the first boxing match that was transmitted, broadcast. By the way, there's a difference between communication and broadcast. Communication is point to point, one transmitter, one receiver, and they talk to each other. Broadcast is a term borrowed from agriculture, and it comes from the term of casting seeds broadly. Just you walk along the field and you throw the seeds out onto the ground, rather than planting each one individually. And it means one transmitter and many people listening to it. So by the end of 1920s, vacuum tubes had brought radio into the entire industrialized world, and vacuum tubes, with their unique ability to amplify, enabled sound movies, phonographs with vastly improved fidelity, test instruments for labs and servicing, and industries benefited from electronic instruments with automatic control systems to regulate processes that would otherwise have been impractical or even impossible. Among the first measuring instruments is the vacuum tube voltmeter, or VTVM, invented in 1922 by E.B. Moulin, M-O-U-L-L-I-N, at the University of Cambridge in England. By using tubes to amplify the measured signal, it has a great advantage over the conventional voltmeter, because the grid of the tube, as I mentioned before, has virtually infinite input resistance. And therefore, it does not load the voltage source. If you use a conventional voltmeter, which is basically a sensitive milliammeter or microammeter with a resistor in series, it has to pull a finite current from the source. And if the source has a big internal resistance, you're going to suck the voltage down and get an inaccurately low reading. In addition, an additional advantage is that the limited plate saturation current protects the meter movement if a klutz like me shoves in 100 volts on the 1 volt scale. You may peg the meter, but you ain't going to burn it out. Years later, RCA marketed vacuum tube voltmeters for the radio and TV repair industries. And this is the senior volt-ohmist, which is at the Sarnoff Museum. And it is a typical service grade vacuum tube voltmeter. Another important electronic instrument is the signal generator. It uses an oscillator to produce a test signal of constant frequency and a calibrated amplitude, and an audio oscillator to modulate it. And it gives you a known signal of known amplitude and frequency to test radio receivers. Evolution continued. Tube became more compact, more efficient, more reliable, and more economical, eventually with thousands of specialized types. The handout lists a couple of the tube handbooks, which list literally thousands. The vacuum tube enabled us to broadcast voice and music via radio, talking movies, quality audio for recording, public address, then TV, radar, and the first electronic computers used vacuum tubes. These inventions connected the world as never before. Vacuum tubes were thus the fundamental invention that created the electronic age. And now, folks, if you have any questions, I would be glad to do my best to answer them.
Sorry, I was took me a second to unmute. We do have a few questions that are actually still kind of trickling in, but I'll start with this first one. Is the cathode and filament separate in the concentric triode?
Well, obviously, there are both kinds of concentric triodes. Some of the earlier ones had a conventional a conventional filament, which was also the electron emitter. Others have the more modern tubes have the indirectly heated cathode. The only tubes that in modern times use the directly heated cathode, or the filament as the emitter itself, are battery tubes used in portable equipment, where you want to absolutely minimize the drain on the A battery, and also in high power transmitting tubes where you need to get really a lot of emission, and you want to enjoy that really high temperature of the filament itself. And there, the 5 volts or something across the filament is not going to make any big difference to the RF, because you're dealing with thousands of volts on the plate. Okay.
Yeah, no, that sounds great. Thank you for that. I have another one here. Could you discuss the characteristics of beam tetrode versus pentode?
Ah, yes. Well, the beam tetrode is a tube where you, instead of using a suppressor grid, you form the electrons into a collimated beam, which essentially, I guess, drives the electrons back to the plate. It avoids that problem. And for really high power, the beam tetrode is, in fact, a preferred tube. The high power audio and radio frequency tubes use it. The first popular beam tetrode was the 6L6, which is still popular, by the way. It was introduced in the 1930s, and we still use them. The references I have, I don't want to go, it would take a long time to explain all the details, but a couple of the references I have, for example, let's see. Frederick Terman's book is excellent on that. By the way, he was not only a great engineer, but he could write in comprehensible language. So that I'd suggest you, rather than take a lot of time here, he talks about the beam tetrode in considerable detail in his books, and almost any electronics book would have some on that. But the idea is that by forming the electrons into a beam, you avoid the need for this suppressor grid.
We'll say one thing about scholars: they're brilliant, but some just don't know how to write, and that makes it even harder to communicate that brilliance.
You ain't kidding. You ain't kidding.
There's some good comprehensible books out there.
That's one of the reasons why I think it's quite important to have liberal arts as well as a technical education. Take courses in English composition and in history, so you know where all this fits into the world. And I mean, how many great ideas have been lost because the inventor couldn't express clearly what he had to say? Good point.
Numerous. I have another question here. It may require jumping back to an earlier slide, but it says, in one of the earlier slides, the tube geometry was characterized as concentric, but the control grid appeared to be of oval cross-section. Was there an advantage to the oval?
Let me crank back and see if we can find that. Here we go. Yes, I think the idea was that you wanted to have, instead of just maximizing gain, you wanted to have uniform gain over a wider range of grid voltage. And by having some of the grid closer to the cathode and some of the grid further from the cathode, I believe you achieve that. In other words, you get a tube which is more linear and hence more suitable for, say, high fidelity without having to use negative feedback and other tricks like that to stabilize, to linearize it.
And then I actually have another question here from our former curator, Flory, and she's asking, the age of the vacuum tube seemed to continue even after the invention and even the drop in price of the transistor. Why was that? And when and why did the transistor overtake the vacuum tube, at least in consumer electronics?
Excellent question, Flory. Thank you. Glad you made it and could show up. I'm going to crank back to the just a minute.
Oh, you are still muted, Jonathan. Here.
Oh yeah, that's what. Okay, I'm okay. Thank you. All right. The transistor first showed itself in portable equipment, which had to operate on batteries. And the early transistors could not handle high frequencies very well. They didn't handle high power, but they didn't require a filament supply, and they operated on low voltage, maybe 10, 12 volts or something like that. So the first devices were things like portable radios and hearing aids and other equipment where you just needed something that drew a lot less power. And obviously a transistor is much more compact than a vacuum tube in general. Transistors took over as transistors got better. They could handle higher frequencies. They were more reliable when silicon replaced germanium as the dominant semiconductor. They were less subject to burnout, and they don't age the way tubes do. Even the best tubes, the filament the cathode eventually loses emission, and the tube gets weaker and doesn't last forever. I mean, they last quite a few years. I mean, every time you turn on your radio, you don't have to replace the tubes. But the transistor, as I said, operates on lower voltages generally. It can be it's much more compact. It's much cheaper. I mean, transistors now cost pennies a piece, and you just cannot make vacuum tubes that cheaply. So there's some of the reasons. And why do vacuum tubes persist? Okay, there are several places where they do. One is high power RF. Here's a tube similar to the one I was showing before. This is just about a 50-watt tube. When you get up to thousands and thousands of watts, given the highest RF power that a transistor can handle is, say, a couple hundred watts, you need to have zillions of transistors. And we've seen the phenomenon on RF generators where people went to solid state when they shouldn't have. And you have the transistors in push-pull pairs feeding into combiners and all of that kind of thing. And one day, one transistor says, oh gosh, I think I'm tired. I think I'm going to burn out. And he burns out. And he pulls down his push-pull partner with him. And the other members of that combiner get overloaded and they fry. and the next one, and a chain reaction, it's usually 2 to the n, say 64 transistors are fried. You spend the next week soldering in, soldering in new transistors. Yes, it's happened to me. There wasn't 64, but it was, I think it was 16. So when you get into tens of kilowatts of really high power tubes prevail. Of course, there are specialized tubes for microwave and that kind of stuff. And then you've got, audiophiles who, for aesthetic reasons, happen to like the sound of vacuum tubes. Although in a linear amplifier, I'm not sure anyone could really tell a difference. But one place where you can is, say, in a guitar amplifier, where you use in the electric guitar, where you drive the tube to overload. You drive the amplifier to overload, and it causes a particular kind of distortion. And the idea is that a transistor, when it reaches its saturation, cuts off with a sharp peak, a flat top, whereas the tube is more rounded. And so you don't get as much of the higher order overtones, harmonics. And it has a particular quality that is associated with the electric guitar, which was invented in the 1930s, by the way, with the 6L6 tube. And I think they still like 6L6s or related types for guitar amplifiers. And some of the vacuum tubes are also much more resistant to electrical overload. A field effect transistor has a few atoms thick layer between the gate and the source and drain, whereas a vacuum tube has a few millimeters of absolutely nothing. And it's rather hard to burn out absolutely nothing. So if you accidentally, that's why, by the way, why that amplifier I have is vacuum tube. Because if I'm looking for microvolt level signals and I accidentally hit it with tens of volts, I'm not going to fry anything.
Well, I think we're gonna close with just like 2 more questions here. And then I think I just lost it. Oh, here it is. I've heard of something called a cold cathode tube. What are they, and were they used in signal processing?
Not really. Cold cathode tubes are usually used as voltage regulators. They're not vacuums in the strict sense. They're filled with a gas which ionizes. And it turns out if you arrange the gas pressure and geometry correctly, the voltage drop across the tube is essentially constant over a wide range of current. So, for example, if you have a power supply and you want to you come off your power supply, have a series resistor, and then feed to a VR tube, even though the load on the supply may change, and even though the power source for the supply, the line voltage may change, the output voltage remains very nearly constant. And by the way, the oscillator in a super heterodyne receiver, or any oscillator that you want to be ultra stable, likes to have constant voltage. It's equivalent to the Zener diode. It's a vacuum equivalent to the Zener diode as in its ability to regulate voltage. And there are also some tubes that are gas filled that are used for triggering, similar to the thyratron usually has a hot cathode, but they're gas filled, and when the gas ionizes, you get an avalanche effect, and they switch on instantaneously, handling very high currents. They have both mercury and hydrogen thyratrons. If you really want to switch fast in sub-microsecond, obviously hydrogens are a lot more mobile than mercury, which is, although named for the god of swiftness, big and fat and heavy compared to hydrogens. Yeah.
And I think that our last question, I'm particularly curious about this. I like the sort of interdisciplinary approach here. So the question is, how do the tubes used for medical x-rays of the 1900 to 1920 period relate to the radio tubes we were discussing in this presentation?
Well, some of the early X-ray tubes did have a residual gas in them, but we'll talk about a high vacuum one. Yes, they're diodes. You have a filament or cathode at one end, and down the other end of the tube is an anode, which is jacked up to tens of thousands of volts. And what happens is that the electron flies off the filament to the positive anode and strikes it. And this generates photons, which have an energy comparable to that of the electron that strikes. So you end up with 50,000 electron, if it's 50 keV, no, 50 keV photons, which are in fact X-rays. And so it's they are basically the diodes. In fact, when you operate transmitting tubes at voltages much more than 10,000, you want to be a little cautious about generating X-rays. I remember I had a consulting client who was operating a really high power vacuum tube oscillator for testing components, and it was running tens of thousands of watts. And I think it had 10, 15,000 volts on the plate. And she was a little bit worried that there might be X-rays. So I borrowed from the dentist, I mooched from the dentist, some dental X-ray film. And I put a piece near the tube, and I put a piece of lead in front of half of it and no lead in front of the other half. We ran the tube for maybe a half an hour, and I took it home and developed it. I do photography, so I was all set up to do that. And fortunately found that there was no difference, there was no relative darkening in the part that was not shielded. And so in that case, we did not have X-rays, but at least it put our minds at ease.
And actually, I think
Oh, and by the way, TV picture tubes can generate a very small amount of X-rays, and that's why they use leaded glass often for the screen to prevent that from getting out. Yeah, go ahead.
Sorry, I said I was saying I think I lied. There is another question on here that sounds kind of relevant as well. It's what is the shelf life of a tube?
Well, I don't know. Let me see. The universe came into existence about 14.5 billion years ago. No, I have tubes that were made in at the museum. We have tubes that were made in the 1920s or early 30s, and they're still happy. Now, these tubes have in them a material which is called a getter. And it's a metal which forms stable oxides with both oxygen and with nitrogen, which are the two dominant air gases. And so if a few air molecules manage somehow to diffuse through the glass, the getter gets them. That's why they call it a getter. And that's a silvery deposit you find on the inside of tubes. In transmitting tubes, the getter is often coupled to the filament. It gets hot and it eats up the residual gas. That's why you're supposed to light the filament for on a tube that you've never used before, that's been sitting on the shelf a long time. You're supposed to light the filament for half an hour or an hour before you hit the B+. I lost the tube once because I didn't do that. But anyway, but it's essentially forever, unless there's one poison that will blow away the vacuum of a vacuum tube, and that is helium. And on tubes that are meant to be used in laboratories where helium may be present on the box, they always give you the warning: do not let this tube see any helium, or it'll diffuse through the glass and it'll ruin your vacuum. And in fact, I once was operating a laser which would lose helium neon laser, which would lose its helium because it would diffuse out through the glass. And so the answer to that was I put the laser tube in a container, just a plastic bag, and then fill the plastic bag with helium and let it sit for a day or so, and then put it back in, and son of a gun, it was happy again. So with the exception of helium, the seal on a vacuum tube is really, really good. So we can talk about many decades.
Well, that was really a great talk. I'm not sure if Margaret wants to add anything before we close.
I think we are good. I should just note that we will post the talk to the Sarnoff's YouTube channel. It will probably take me a few days to get that up, but that will be up and captioned hopefully by the end of this week.
Oh, great. So it's going to be you made a movie of this?
Yep. Yeah,
Oh, good.
so you'll be famous on the internet.
Oh, thank you. So and it's a talkie movie, so that's thanks to vacuum tubes.
Yep. So, but thank you all for coming. I'm so glad actually that it was an internet event because it's snowing harder and harder out the window today. So we picked the right media for today. But thank you, Jonathan. Thank you, Ryan. And we will
A lot of fun.
Yeah, it was. And we got some good questions. I'm really happy about that. Thank you all for tuning in and take care. Stay warm.
Okay. Yep. Goodbye. Take care of
Thank you,
yourself,
Jonathan.
guys. Bye. Thank you.
Everyone.